Hello out there and welcome to 3D Printer Fundamentals. My name is Don McLaughlin. I'm going to start out with a little background of where I come from and what my experience is. I graduated in 1975 from Lakewood High School in Lake Odessa, Michigan. That year, I went to the Plymouth Troubleshooting Contest. Uh, I was chosen, me and one other guy was chosen to go to the contest from the auto repair shop, and that was my first little bit of troubleshooting. Um, Basically, I've been trained as a troubleshooter for most of my life. I got a job right out of high school at Pontiac dealership in Battle Creek, and I was certified mechanic when I started working there. And in 1980, I got a job at Fisher Body in Lansing, working for GM. I started on production and worked there for 14 years, and then I went on the skilled trades apprentice program and became an electrician. And for the remainder of my time at GM, I was an electrician working on robots. And for the last 5 years, I taught robotics, uh, mostly spot welding and communications between the cell and the robots, and some FANUC robot classes. Um, that's pretty much my background. Brian asked me to put together this 3D printer fundamentals for some of you folks out there. They're kind of timid about them. They're really the best application as far as a robot um, working, how a robot works in the real world. It's a pretty good example. So anyway, I'm going to continue on now, and we're going to show you. This is the Ender 3 Pro here. That's me up in the corner. Um, the Ender 3 Pro is by Creality. Creality makes a whole bunch of different printers. This is one of their cheaper printers. This is a printer I bought and I've been using for the last 6 months. Um, it's really reliable. I've ran it almost every day for the last 6 months, and I've had to work on it, of course, because that's the way machines are. But other than a few minor glitches here and there, it's been very, very, very dependable. Um, when I saw the 3D printer, it looked like this um, on the internet. My wife actually purchased it thinking she was going to be able to make masks for the COVID thing. But when we got the printer, um, of course, it looked like this. So it was not something that was like already ready to go and set up. You have to set it up. You have to put it all together and do all of the fine work as far as getting it to work properly. But don't let that scare you. I'm going to start out with some of the components here, tell you what they do, and then I'll show you how the thing actually works, fundamentally works. This is the readout plate on the Creality printer. It's an Ender 3 Pro, obviously. It takes 270 watts to run it. The build plate size is 220 by 220 by 250, which is approximately 8 inches by 8 inches by about 10 inches, maybe. And it runs on 115 or 230 volts. Just depends on what you got to run it with. This is the power supply that it comes with. This is a 120 volt to 24 volt power supply. The newer Ender 3 Pros are 24 volts. The old Ender 3s were actually 12 volts, but you can use smaller wires the higher voltage you go. So this is a good improvement. Actually, this is one of the newer power supplies that are supposed to be really dependable. I haven't had any problems with it so far. This here is the x-axis, and two of the three axes run with these belts here. Toothed belt. You can see the diagram at the top there, or the little arrow pointing down to the tooth belt, and there's a geared pulley on the end of this motor here. Um, that runs it. These are all stepper motors, um, basically just little bitty small robot motors is what they are. They have a built-in encoder, so they know where they're at. But they have to be uh, auto homed every time you turn them on because they lose their counts on their encoders. So you have to remember that to always when you start up the machine, you have to run auto home. Like I said, this is the X. This is the X motor, X-axis motor. This is the Y-axis motor. A little better picture there of the um, toothed gear on the end of the motor and the belt. The belts are fiberglass. They're also tooth belts. They last seem to be lasting a long time. They haven't had any problems with them yet in my 6 months of running them, so they're pretty dependable. And this is the Z-axis motor, and the Z-axis motor actually runs a lead screw there, and that runs the bed of the printer up and down for the Z-axis motion. And the last encoded motor is the extruder motor. And this is what actually drives the filament down into the hot end head where it actually puts the plastic out to the bed. And you can see there's a little tooth gear there, a little bronze gear, and the filament rides between the gear and a little pulley there that's spring loaded on this arm. This is the metal version of the extruder um, assembly. It comes stock with a plastic one, but I read right off the bat that those are prone to cracking, so I went ahead and upgraded to the metal extruder assembly. Um, there's two different types of extruders. There's the Bowden and the direct drive extruder. On the left of this diagram, you see the Bowden tube setup where it's actually the extruder assembly is off to the side and it has a tube, a PTFE tube that runs over to the hot end assembly to carry the filament over. The other type is a direct drive system. I actually took the Bowden system off of my printer and put a direct drive system on because you're able to print more types of materials with it, rubbery materials and stuff. So that's an upgrade that I've done to my machine, which is really helpful. Now, this is how the two axes work, the X and the Y axis on this machine. They have three um, rubber wheels, and two of the wheels are just bolted in, and then the third one has a cam screw, which actually moves the wheel in and out towards the rail back and forth. Also on this diagram, you can see the belt that lays inside of the rail there, just a little bit on the right. And that's what runs this carriage. This is the X-axis carriage back and forth. This is before it has a hot end or anything on it. This is the um, where the control motherboard is. It's covered in a little case, and there's a mini USB port and a micro SD port. Now I've made a little change on the micro SD port. I got an adapter that actually will run it with a regular SD card, so I can put the micro SD card in a regular SD card holder, and it's a lot easier for me to hang on to, put in and out. But a lot of people use just a hook up right to the computer, and I think that's what the school is going to use too. It's using is a mini USB plug right into this to the computer that controls it. This is the main control panel as far as uh, running the thing. This is how you run it. You use this little button here to you push it to select to what menu you want to go into, and then you turn it to browse on the menu itself. It's a menu-driven system, and you'll have to learn that on your own. I can do a menu map later on, but right now I'm just covering these basic things. I do have this to show you. It tells you uh, what the items on this initial screen um, tell you, and that's uh, starting at the upper left there, hot end temp in Celsius. Everything is metric on this thing. Um, it has the bed temp in Celsius, material cooling fan, speed indicator, percentage completed, start time since starting there. That's how long it's been since you started the project. The message readout will actually put different messages up depending on what's going on with the machine at the time and what you have programmed it in to have it say. And also the X, Y, and Z there is the axis position indicator. And when you first turn on the machine, this screen comes up and the X, Y, and Z's are all flashing question marks. That means you have to run the auto home function, which is one of the things you have to do every time you start the machine. Like I said, it loses its memory, so you have to reinitiate the home to it. This is two hot ends here, the two different type of hot ends that are used with this particular machine. I put a new, the one on the left is a all metal hot end with a titanium brake tube. Titanium doesn't carry heat very well, so they use that in between that and the hot end where the heat is at the bottom there, where the tip is, and the cooling area. The cooling area is above the titanium brake tube there. The blue line there represents where the Bowden tube ends up inside each of these hot ends. The one on the left, the Bowden tube stops at the top of the cooling section, and the one on the right, the Bowden tube, goes all the way down to the tip, the nozzle, and it actually touches the nozzle and butts up against it. The nozzles are brass. The standard nozzle size is 0.4 millimeters, but you can get a nozzle anywhere from 1 millimeter all the way down to 0.1 millimeters, which is very fine. So there's a lot of different options for these machines. Now remember, this is just one. There are literally dozens of different uh, 3D printers out there, and they all are a little bit different, but the fundamentals are the same. This is another look at the hot end there. Um, the hot end, the one on the left is showing the stock hot end that comes with the Ender 3, and it comes with the Ender 5 too. And the Bowden tube goes all the way down. You can see there that it's going all the way down, and they're talking about a partial clog from back pressure. And so on the right is a little fix for that, a modified stock hot end, it's called. And I actually use this fix on my hot end, and it does seem to prevent plugging problems. Now, this is not a plug and play type thing, and it will not. You're going to have to work on it as things mess up. That's just the nature of the beast. There's nothing you can do about it other than just figure out what's wrong and go on from there. It's relatively simple, though. There's not a lot of moving parts and stuff, so it's not that hard to figure out. Mostly, the biggest problem with it is getting uh, clogged on the end, and then the extruder stops feeding material down. I've also had one instance where I actually had a piece of metal shaving that was embedded in the filament, and it's got stuck up in the tip because the filament is actually 1.75 millimeters, but the tip is only 0.4 millimeters, so it squishes out. It has to go down to a smaller size to get out of the tip, and that metal shaving that was in there was too big to get out of the tip. So little things like that are going to mess you up no matter what's going on. That's just the way life is. Okay, now this is the actual hot end assembly, and the Ender 3 Pro that I have and the Ender 5 use the same hot end assembly. There's two fans on it. On the left is the uh, cooling fan for the hot end itself. It blows across those cooling fins and keeps the upper part of the hot end cool so the filament doesn't melt too soon. You want to have a controlled melt on the filament, and that's what this fan does. The fan on the right, the material cooling fan, is a squirrel cage type fan, and it just blows out of the bottom and onto the material as it comes out of the hot end. So it cools the material as it's coming out. Um, PLA, you use this fan all the time. ABS, you don't use this fan at all because ABS likes to warp, pull up from the bed. Personally, I like PLA the best, and that's what I use most of the time. I've used a little ABS, but it's such a pain that I prefer PLA. And PLA2 is even better, works even better than PLA. So I'm kind of stuck on that material. But you can use other materials. They have nylon, they have carbon fiber, they actually have a wood uh, filament that looks like wood and you can stain it. So there's a lot of materials available out there. This is the actual bed of the 3D printer, and this is not the stock bed. I have done upgrades on my 3D printer. This is actually a borosilicate glass bed, and this is by far a superior bed surface for a 3D printer. The printer that or the bed surface that came with the printer was PEI, which worked relatively well, but it followed the contour of the plate underneath, and the plate underneath was warped. So it did not print very well. So I upgraded and I got a new plate, a new glass plate here. There's an aluminum plate underneath it. And I also got a new bed heater, a silicone bed heater instead of a PEI bed heater, which heats up much faster. Uh, in order to get stuff to stick to this plate, sometimes depending on the color, and it's a color thing, whatever they use to color the different filaments, depending on the color of filament, you have to use some, I use Magic Goo, it's called, which works great for sticking the filament down and then releasing it when it's cool. The bed heats up, depending on your material, the bed heats up to 60 degrees Celsius. I didn't mention the temperature of the hot end, but the hot end gets up to 210 Celsius for PLA, and it can go up to 260 Celsius. That's about the extent for the hot end I have. Um, that's the reason that they use the metal hot ends, is because you can use a higher temperature to do more exotic materials. So this is your glass bed. This is actually this moves with the z-axis. It's hooked up to the z-axis, and this picture here shows you underneath the bed. You can see a little bit of the heater pad that's glued onto the back of the aluminum plate, and there's 4 adjustment screws here. This is the most critical part of a 3D printer, is getting the bed level and at the right height to the hot end. I cannot stress this enough. You have to have the bed level, which is level is perpendicular to the hot end tip. That kind of level. So that you have to set it up to be a certain distance away from the hot end, and that distance I found is well, that's coming up. But here's a picture of the adjustment wheels from the bottom. You can see the adjustments wheel there, wheels there. There's 2 of them. There's another one over there to the right, and also you can see the heater element there, the bottom of it, that kind of pinkish stuff. And you can see the track wheels there, the guide wheels on the actual rail that the y-axis uses to run back and forth. Now, here is the actual workflow chart that tells you what you have to do to get a 3D print. First, you have to have a CAD 3D modeler program. I use TinderCAD. It's free on the internet. It runs through your browser. I use Chrome browser, and it runs through that just fine. And use with that or whatever CAD 3D modeler you want to use, you have to make an STL file. Now, there's several different types of files that are 3D files, but STL files just one of many. Cura, the slicer program that's coming up next, uses several different types. So from the STL file, once you make that, you import that or you load it into the slicing application. And in this case, for this type of printer, you use Cura. And Cura is an open source, free slicing program. It works great. It has a lot of variables. I'm going to do another presentation on how to run Cura and try to get you up to speed on that too. It works wonderfully. I can't say enough about it. But that is what actually takes the STL file and your object, and you set that up with the slicing application on the bed of the printer, and you show it how you want to print the actual objects. Excuse me. With Cura, you can move the object around just like you can with the 3D modeler and get it placed on the bed just the way you want it, so that you have the least amount of waste. And I'll get into that later, but there is some waste with 3D print sometimes when you have to have supports made. So from the slicing application, it makes what is called a G-code file, and this is the file that ends up having the layer slices and tool paths in it. They're showing in the next part of this flow chart, and that file goes over to the 3D printer. And then from the 3D printer, you run the G-code file, and it prints out your object. It's just like magic. It's incredible how fine of detail that these 3D printers, especially this one, is a cheap printer, makes. It was really hard to believe when I first started making things. So anyway, that's how you get a 3D object out of your 3D printer. This is the actual way that the printer sees in where it's at in space, and this is also, it's called Cartesian coordinates. And it's also how robots in the real world work. I've worked with ABB robots, I've worked with FANUC robots, and they all use Cartesian coordinates. Now, this particular printer here, we only use the plus side of the Cartesian coordinates. So you're only using the plus Z, plus X, and plus Y here. And the 0 point is actually the home point for the printer. And the printer actually goes to home automatically, and there's 3 limit switches for each axis, and when they touch down on the limit switches, that is 0x, 0y, and 0z. Like I said, this is how all robots work. They have other printers that are called delta printers that don't use Cartesian coordinates, but this is the best example of closest thing to a real life robot that you're going to see without having to spend $30,000 for one. Okay, there's a little explanation here on how that system works. The G-code file, once it's in the printer is told by the G-code file where in space it needs to go for making different items. And the points are called X, Y, and Z points. And this is a perfect example because 0 there is the home spot for the printer, and then everything else is plus X, plus Y, or plus Z. Very important. This is a very important thing here too. Once you get your bed leveled, you have to make sure that as you're leveling, that you have the correct distance between your hot end and the bed surface. And that's what this diagram here is showing you. The top one, the hot end, is too far away, and you're only getting bare minimum of contact on the surface there, just on the bottom of it's like a tube of toothpaste spitting out, and you're only getting a little bit on the bottom of the curve of the line there. The center one is perfect. It's smooshing out a little bit on the sides, sticking down good to the bed, and that's what you want. The bottom one, if you get it too close, you can actually end up scraping the glass, and you don't get good adhesion that way. You don't get enough material on the bed itself. So that's a very important aspect of this, is that you have to get the bed leveling down to the right distance from the hot end to the bed in order to have a good print. Very, very important. Probably the most important thing that you have to set up with the 3D printer. And here it's showing you a little better diagram of that distance there. And when I got my printer, all the literature and stuff said just use a piece of paper from your copier to set this distance here, and that doesn't work for me. You got all this other technical stuff here, and you're telling me to use a piece of paper to set it. So finally, I searched and searched, and I finally found out that the actual distance is zero point 0.1 millimeter, or I use 3 thousandths because that's the what I found best for the zero point 0.4 millimeter tip. Now, if you use a different tip, this is not going to hold true. If you have a different tip, you have to set the bed leveling at a different size according to the tip. Okay, now that's pretty much the fundamentals of the uh, 3D printer. Um, One great place to find information, I found a ton of information, is right here on filamentfriday.com. You go on YouTube and type in either CHEP or filamentfriday.com, and you will see this icon pop up. And this guy is mostly he works with the Ender 3 Pro or the Ender 3 products, so it's a real good reference for that. But he does have a lot of information that's not necessarily just specific to the Ender 3. So go on and check this guy out. He's got over 150,000 followers. There's a lot of people that use him, and he has great information. He's one of the best guys out there on YouTube. And I hope this helped you out some. You you make sure and have a good day, and I'll talk to you later. Thank you.